Hello everyone, this is Chen from Northwestern Polytechnical University. Today I'm presenting our poster, an optical MEMS sensor for dynamic wall shear stress measurement in complex flow. We target dynamic near-wall measurements in challenging flow environments by combining a floating MEMS structure with a differential optical readout for robust high bandwidth sensing. Wall shear stress is a key parameter for characterizing near-wall flow phenomena, especially in high-speed boundary layers where it fluctuates rapidly and reveals transition, disturbances, and vortex evolution. Conventional electrical MEMS, sensors capacitive, piezoresistive, or piezoelectric are mature, but suffer from electromagnetic interference and intrinsic bandwidth limits. Optical sensing, by contrast, offers non-contact operation, strong EMI immunity, and broad frequency response, making it attractive in harsh, interference-prone environments. Here's the sensing principle. The device uses a rectangular floating element supported by four folded beams and suspended in a cavity. Metal gratings are deposited on the back side of the floating element and on the cavity bottom. When wall shear stress drives a tiny displacement of the floating element, the relative grating alignment changes the detected optical intensity, giving a differential, non-contact displacement readout that is naturally immune to EMI. To balance sensitivity with speed, we performed multi-bijective genetic algorithm optimization of the floating element and beam geometry. The result yields a theoretical first resonance around 10.4 kHz while maintaining sufficient mechanical sensitivity, setting the stage for high bandwidth measurements. The fabrication is SOI and glass-based. We set the device layer cavity in SOI by ICP sputter CRO to form the floating grating. Wet etch a cavity in BureauFloat 33 glass with HF and deposit the fixed grating. Then perform anodic bonding between SOI and glass. After bonding, we remove the silicon handle and barium oxide and release the floating element by ICP. The fabricated chip is about 5 millimeters, and the final package footprint is 12 millimeters, facilitating integration. For static calibration in a laminar channel, the output shows excellent linearity or squared greater than 0.999. The measured wall shear sensitivity is 4.83 MVPA, and the static non-linearity is 1.71%. Noise floor testing at 1 kHz indicates 7.69 micro VHC 1/2, corresponding to a minimum detectable wall shear stress of about 1.6 MPa. These results establish both accuracy and fine resolution at small signals. We then characterize transient response using a shock tube. The step-like shear excitation produces a clear sensor response with ringing. The primary oscillation lasts 100 microseconds, indicating a resonance near 10 kHz. Power spectral density analysis shows a dominant peak at 10,495 Hz, an excellent agreement with theory and simulation, confirming the designed high-frequency capability. In shock tunnel runs, the sensor response is consistent across the stationary, diaphragm rupture, quasi-steady, and decay phases. From 3 repeated tests, the relative repeatability error is 1.36%, demonstrating robust dynamic stability under strong unsteadiness. We also test in a Mach 5 hypersonic tunnel with angles of attack at 0, 4, and +4. The sensor delivers stable outputs that reflect the changing direction and distribution of wall shear stress under each condition, verifying real-time tracking capability in complex flows. To summarize, we present an optical MEMS wall shear stress sensor with non-contact readout and strong EMI immunity. Through structural MOGA, the 10.4 kHz resonance aligns with shock tube measurements. The sensitivity is 4.83 MVPA, and the measurement range is 0 to 500 PA. Wind tunnel validations confirm reliable detection of unsteady wall shear stress with a 1.36% repeatability error. These results support applications in high-speed, unsteady environments such as shock tunnel diagnostics and scramjet combustion monitoring. Thank you for watching. If you'd like more details or data, please feel free to contact me by email after the session.